Okay, we are ready for chemical bonding, Lewis dot structures, naming compounds, and writing formulas. And here I'm going to wobble the camera a little bit. Ooh. Okay, so these are, if you were unable to be here for the notes in class, or you're homebound, or you just need to review. These are the notes that we're talking. These are the notes that you're going to handle here. So the state of Texas says that you're going to have to be doing several things here. First and foremost, you have to name ionic compounds, covalent compounds, acids, and bases using IUPAC rules. Then you also have to write the formulas of what I said before using the IUPAC rules. But that's not all. You have to construct electron dot formulas and illustrate ionic and covalent bonds. You have to describe the nature of metallic bonding and apply the theory to explain metallic properties like thermal conductivity, electrical conductivity, malleability, ductility. And you have to predict molecular structure, but only 3 basic types. You have to do linear, trigonal-planar, and tetrahedral. And that's the geometry, and we use these little valence shell electron pair repulsion theory. Whew. Okay, so let's talk about some bonding. And we have a lovely little comic for you, so take a minute and read that. Enjoy. Some of you guys need to suit up like this when you're in lab. All right, we'll start off with covalent and ionic bonding. Chemical bonds are forces that hold atoms together. So these are the things that hold the atoms together so that they stay and make one compound. And we follow the octet rule. We've talked about this in class before. What's the magic number? The magic number is 8. For some reason, when you have atoms bonded together, when the atoms develop a number of valence electrons of 8, they're stable. Now that's the vast majority of them. There are a few exceptions, but we don't have to worry about too much about the exceptions just yet. So their chemical compounds tend to lose. What did I write here? Excuse me, I have to read that again. Chemical compounds tend to form so that each atom gains electrons, shares electrons, loses electrons, transfers electrons, whatever it is, has an octet in its highest occupied energy level or orbit. Okay, that's doing weird stuff on me. Let's just go on. All right, atoms bond and redistribute their valence electrons to make the atoms more stable. The whole purpose is to make things more stable. Nature tends to move towards a lower potential energy, less stored energy, and it becomes more stable. There are 3 major types of bonds that hold the atoms together in the compound. And these are called intra means inside, intramolecular bonds. So when you look inside the molecule, or the formula unit, what's holding those atoms together inside there? So we have ionic bonds, and ionic bonds transfer the valence electrons. The metals always give away the electrons, the nonmetals are always taking the electrons. Covalent bonds, they're much nicer, they share. So we can have bonds between the nonmetals, and they don't mind sharing with each other. They just don't share with the other guys, the metals on the periodic table. You can have polar covalent and nonpolar covalent. Polar means that one of the atoms in the bond is taking just a little bit more than its fair share of the electrons. So one side of the molecule tends to be negative, and the other side tends to be positive. Nonpolar means they're sharing equally. Metallic bonds are kind of strange. They're when you talk about the valence electrons, and they're just swarming all over the place. Whatever atom brought its valence electrons, those electrons didn't stay with them. So they were just, like 70s hippies or 60s hippies or something. They were just free to go with whomever they wanted to. Sometimes they refer to it as the electrons, the atoms are like in a sea of electrons. All right. Intermolecular bonds are bonds between. Inter means between. And those are bonds between molecules. They're not very strong, but they do account for a lot of properties, especially properties of water that we'll talk about later. Hydrogen bonds are the first and foremost of those. That's a weak bond between hydrogen and another atom in a different molecule. Usually that atom is a lot more electronegative. Remember, we talked about electronegativity. When you have atoms in a bond, how strongly do they attract the electrons? Well, if there's fluorine, oxygen, nitrogen, those guys are really strongly electronegative, and they tend to be the ones that hydrogen forms those hydrogen bonds with. Okay, so we have a pretty picture here. This comes out of the chemistry book. how to determine if a bond will be ionic, polar covalent, or non-polar covalent. So we can kind of look at this chart and that'll help us out, but we'll keep it pretty simple. If it's between a metal and a metal, it's a metallic bond. If it's between a metal and a non-metal, it's ionic. And the only ones we really have to worry about are the covalent bonds. If it's between a metal and, if it's between a non-metal and a non-metal, then we have a covalent bond. And we just have to worry about whether or not it's polar or non-polar. Oh, look at that lovely electronegative chart. Notice electronegativity increases as you go up on the group and as you go across on the period. So look way over there at fluorine, how strong it is. It's got a 4 electronegativity. And look way down here in the lower left, and we see francium at 0.7. It's not very much. It's pitiful. Oh, look at the differences in electronegativity to determine the type of bond. The atom with the larger electronegativity will be the more negative atom. So we're talking about polar stuff. And oh my gosh, we have to stop for right now. So we've looked at the different types of bonds, and we'll do a little bit more in the next section.